Hello students, next we are going to look into AC Nortons Theorem. As I had seen the case of AC Thevenin's Theorem, AC Norton Theorems also has no special statement because it is an extension of the DC Norton's Theorem. Okay, now instead of Rn resistance, what we are having here is Zn resistance, not resistance, impedance. So this Zn is called as the Norton's impedance, and as we have studied previously that RTH is equal to Rn, just like that ZTH is same as Zn, or Zn is same as ZTH. The method of calculating Zn and ZTH are the same because they are the same. Okay, so now let us move into the problem of how to solve a Norton's equivalent network at the terminals A and B shown here. See, now if here we have to find out, in general sense, if I have to find out the Norton's theorem, we all know that we have to draw the short circuit and consider this as IN, this current as IN, isn't it? But if I am short circuiting this and trying to find out this current, the problem is I'll have to find out three currents using this mesh analysis if I'm going to use, or even if I'm going to use nodal analysis, it's going to be little bit more complicated. Not complicated, what I should say is it is going to become lengthy. So just like we did in the previous case, here also we can reduce the complexity of the circuit by adding the series and if any parallel elements, so that we can reduce the circuit. So the first step that I will always do is I will reduce the circuit so that I am able to solve it without much confusion. So that's what I'm going to do now. So as you can see, I will write IN as such, I will write here, there is no problem. And now I am going to reduce this whole set. I am going to reduce. How am I going to reduce this whole set is, let me first draw it. I will draw it as a single element. Okay, and I will find the value of that element. And then I will keep the 5 ohm resistance here. So I am basically converting this circuit, or I am simplifying the circuit into this format. So what is the value of this? That is what is something that we have to see. So as I had previously said, these two are going to be in series. Similarly, these two are going to be in series. So I can write very clearly that the series combination of this is going to be 1 plus 2j, and the series combination of this is going to be 4 plus 4j. Okay, just adding, simple addition. Series element can be added up together to get a single element. Now as you can see, both of these are in parallel. Why? Because as I have already said in previous cases also, this terminal and this terminal, they are touching each other because there is no other element in between. Similarly, this terminal and this terminal, they are touching each other. So these two, this one and this, both of them are parallel. So I can say that I can actually write them as a parallel value. So let me do that here. So here I will write that I should get 1 plus 2j parallel with 4 plus 4j. Okay, 4 plus 4j. And when I do the parallel, if you all remember, what do? I write 1 plus 2j inverse plus 4 plus 4j inverse, the whole inverse. This is a simple thing that I have to do. 1 plus 2j inverse plus 4 plus 4j inverse, the whole inverse. Doing that, I would get 1.62 angle 58.24 degree. You can check this by pausing the video and then calculating in your calculator. Please use the calculator to find these values. Otherwise, when you do a problem, you will always have issues with small errors, and you will never understand where you have gone, where you have done a mistake. So anyway, so that value, let me write here. So it is 1.62 angle 58.24, and this one I will write it as, it's already given as 5 ohms. So it is 5 ohms, and the current here is 10 angle 30 degrees. Okay. So now I have redrawn the circuit. So in the solution, the first step is find IN. How do we find out IN? Basically, what is IN first? IN is basically when you short this, and the current that you get here, that is going to be your IN, and that IN we want to find out. See, now there are many different ways in which you can find this one out, because either you use the mesh, or you use the nodal, or even you can use the current division. Why I am saying that you can use the current division? See, there are two impedances here. One is this one, and the second one is this one, and both of them are in parallel. This is parallel with this one. Okay. So if this current is coming, I can basically use the current division rule. I can use the current division rule, and I can directly find out what is the current IN. But since this is a general method that I am taking for your own benefit, what I will do is I will go for the standard method of using mesh analysis or nodal analysis. Mesh analysis is the simplest. I understand most of the students enjoy doing the mesh analysis. So I will write this one as I1 current. Let me see if I have, yeah, that is I1 current, and this is going to be IN current. It is already given, but let me write it separately. Okay. And now my duty is to find out IN. From figure, directly we can see, from figure, directly I can see that I1 is going to be equal to 10 angle 30 degrees, very clearly. Therefore, now I have to only do for the case of second mesh. So from mesh 2, from KVL at mesh 2. So here I am having the current IN going. So this is plus minus. This is also going to be plus minus. So I am going to take from back of the element. So I will get 1.62 angle 58.24 degrees multiplied with I1 minus, sorry, IN minus I1 plus 5 into IN is going to be equal to 0. From which I can write the IN components together. So I will get 1.62 angle 58.24 degrees, that plus 5 is IN, and I will take the minus I1 the other side. So it is 1.62 angle 58.24 degrees into I1. I1 is already, we found out it is 10 angle 30 degrees. Okay. Therefore I can directly write IN to be equal to this divided by this one. Correct? This divided by this one. So let me write that. So what is this? 1.62 angle 58.24 into 10 angle 30. If I solve that using calculator, I will the value as, let me write it, I will get 16.2 with an angle of 88.24 for this one. Okay, now I have to divide that, so I will write, let me take this one a little bit down, that divided by this value, which one, 1.62 angle 58.24 plus 5. Let me, if I do that, I will get 6.01 with an angle of 13.24 degrees. 13.24 degrees. And this division will give me the value of IN as 2.69 with an angle of 75 degrees. So I have found out IN. Remember, I have used the mesh analysis method. You can use the nodal analysis, or even you can use the current division rule. Okay, so that was the first step. Second step, so step 2 is to find Zn, which is same as Zth. So let me redraw the circuit. And now we can see that there is a current source. We know that the current source has to be open circuited. The independent current source has to be open circuited, and if it's a voltage source, it has to be short circuited. So if I remove this current source, okay, if I remove this current source, then actually I can redraw it with only this one element. So let me redraw it. Yeah, okay, so I have redrawn it. Now what can be Zn? Obviously Zn is the combination of 5 plus this value. So therefore I can write straight away without any much delay. I can write Zn is going to be equal to 1.62 angle 58.24 plus 5. Okay, then if we find out the value, we will get the value of Zn as 6.01 with an angle of 13.24. 13.24 degrees. So I have got both IN and Zn. So next is directly drawing. So the third step is directly to draw it. So here I am having my current source, and the Zn I will have it here, and the Zn value is going to be 6.01 angle 13.24 degrees. This is terminal A, B, and this is IN, which is 2.69 angle 75 degree. Okay, so that is what we are having for solving the Norton's equivalent network for any terminal AB. Thank you.